So I want to say a few words about the thin disk model. Um, so this is the classical thin disk papers are Shakura and Sanyaev, 73, Novikov and Thorne, 73. And then there's a Lindenbell and Pringle. When is it? 74? 74. And a Pringle 1981, which is a very clear review of the material. So if you read these, you should be in good shape. So what is in the in the thin disk models? So we picture a black hole with a disk around it that ends at the ISCO. Excuse me. And inside the ISCO is a region that's imagined to have very low density, where the plasma just plunges into the black hole, so-called plunging region. And then out here, the disk is in centrifugal equilibrium. So it's orbiting with frequency omega equal to square root of gm over r cubed. It is got a scale height h, which is small compared to the local radius. So this is thin disk. And furthermore, in these models, there's imagined to be only interior transport of angular momentum. So we don't exert any torques on the surface of the disk. We don't have magnetized winds carrying away angular momentum. We only have what can be modeled as diffusive exchange of angular momentum between neighboring rings in the disk. And this is often modeled using an effective viscosity. So the units of viscosity are kinematic viscosity are length times the velocity. And the only natural length scale here is the scale height. Only natural velocity scale is the sound speed. It's the only game in town. And then we multiply that by a dimensionless number alpha, which describes the strength of the turbulence or intensity of the turbulence. So the idea is you set this thing up, you turn it on, and angular momentum flows outward, and mass flows inward. And I just want to describe a few salient features of the model. So I'm not going to do the entire derivation. And I'm actually going to provide you with yet another Mathematica script, which automatically calculates every alpha disk model known to man or woman. So it's what it winds up doing is giving surface density okay, so this is integral of rho through the disk, central temperature, photospheric temperature or T effective, density at the midplane. It can even give magnetic field strength, optical depth, and the ratio of, say, gas pressure to radiation pressure. So this all emerges from an assumed value for alpha, from an assumption that it's in a steady state, and from vertical hydrostatic equilibrium and radial equilibrium. So the idea is that it's centrifugally supported. Okay, so once those ingredients are in, you pour these things in, you stir, and you can get a solution for all these quantities. And I spent most of my career trying to get away from the alpha model, somewhat unsuccessfully. So I'm not going to derive it, but let me write down an example solution so you can get a sense for how this goes. So this is for a black hole. One finds central temperature 4.3 10 to the 7 K, alpha to the -1/4, m to the -1/4. And here m is the mass scaled to 1 solar mass. And r in units of the gravitational radius to the -3/8. Okay, so this is for a black hole that's accreting close to Eddington. And this gives us central temperature, effective temperature. So the temperature at the center, at the midplane of the disk, and temperature of the photosphere. This looks impossible because the photospheric temperature is higher than the midplane temperature. But that's because I haven't scaled this to appropriately. Okay, so this relation, which describes the effective temperature of the disk, you'll notice is independent of alpha. It contains no power law dependence on alpha. And that's because the effective temperature is basically determined by an energy conservation relation. So if you're accreting at a certain rate, you need to release a certain amount of energy per unit area in the disk, and that determines the effective temperature, or alternatively, the surface brightness of the disk, which is sigma T effective to the 4th. We can also calculate P gas over P rad. And this turns out to be it turns out to be rather small. So this implies that in sort of stellar mass black holes, close to the ISCO, stellar mass black holes that are accreting close to the Eddington rate, the radiation pressure dominates the gas pressure. So this tells you immediately that radiative interactions with the gas are dynamically important. Okay. So, yeah. Where? Here? 21 over 8. So don't write this down. Please don't write it down. I'm going to give you this Mathematica script, and you can just pull up the solution in there. Okay. Maybe you don't use Mathematica. Anybody can use the command line. Okay. So so you should be able to pull the solution out of that. All right. So this gives you a sense for sort of the power of the alpha model and why it has persisted for so long. If you know what alpha is, if the assumptions behind the alpha model are correct, that you only have this diffusive transport of angular momentum, and if alpha is constant, then this indeed is the run of temperature and ratio of gas pressure to radiation pressure and so on in the disk. So it's powerful. It can give us all the run of all these physical quantities inside the disk. Okay. Part of the notion um, underlying the alpha model is that there's turbulence inside the disk, and I talked about that earlier, and I showed you a simulation of magnetically driven turbulence in a disk. And I'm going to tell you where that comes from, and in particular do the analysis of the magnetorotational instability very quickly in sort of simplified form. So magnetorotational instability is a linear instability of a fully ionized magnetized disk, and it grows by exchanging angular momentum between fluid elements. So it's really exactly what one needs to drive turbulence inside accretion disks. So the physical picture that one has is, say our black hole is here, and we have a disk here that starts out with a field line going through it. And the MRI tells us that this situation, where we have a nearly vertical field going through a disk, is linearly unstable. And it produces streaming of the fluid by coupling together fluid at different altitudes magnetically. So this piece of fluid runs outward and drifts backward in its orbit, and is further torqued by the by the magnetic field. So this bend in the field line produces a force that's directed inward on the fluid element and directed forward along the trajectory. And this bend in the field line produces an outward force and a backward force. It removes angular momentum from this fluid element as this instability develops. So there's a characteristic frequency associated with this disturbance in the field line. Yeah. Yeah. So typically we expect that close to black holes, the the resistivity, the plasma is going to be fully ionized, and the resistivity is going to be sufficiently small that the resistive decay rate, which is something like eta k squared, is going to be very, very small in comparison to the other dynamical frequencies of interest. So things like omega. You can define a yeah. So so black hole accretion disks are typically very, very hot, and at least within thousands of m of the black hole are well coupled to the magnetic field. So you can define a dimensionless measure of the importance of resistivity by taking this to be 1 over h squared. Okay, and where h is the scale height of the disk. And so so h, I have to tell you more. H is cs times, cs over omega. And so the dimensionless number is CSH over eta. So this has dimensions of a diffusion coefficient, and this does too. And this is enormous everywhere in black hole accretion disks. Now, when you go to far out in black hole accretion disks, and the temperature gets sufficiently low, and how low that is depends on exactly what the density is and so on, but probably means thousands of Kelvin or maybe 1,000 Kelvin. Then resistivity starts to play a role. Possibly. So this is a situation that has been extensively considered in protoplanetary disks. And yeah, if it's cold enough, it is decoupled. And there definitely are places that are too cold to interact with the magnetic field. But then there's this set of interactions can occur that Phil talked about, non-ideal terms in the induction equation. So there's not only resistivity, there's ambipolar diffusion and Hall effect. And Hall effect, for example, can be destabilizing in certain circumstances. So it's hard to draw a bright line. I would say that if the temperature is below 2,000 Kelvin, you should worry about how well the magnetic field is coupled to the plasma. Okay, so very quickly, I wanted to mention that there's a simple mechanical model of this process which doesn't involve doing linear analysis of the MHD equations. Okay, so that simple mechanical model imagines two masses that are in a nearly circular orbit with frequency omega around a central body. And these masses are coupled by a spring with spring constant K. And you remember from introductory physics that that spring has a characteristic frequency which is square root of K over M, right? I'll call that characteristic frequency gamma. Okay, so so in this model, we're going to take these masses that are very close to a circular orbit, and we're going to perturb them, and then we're going to look for the modes. Okay, and the easy way to do this problem is to write down a Lagrangian. So the Lagrangian should be very familiar to everybody. Okay, except that I'm going to add one new term for the interaction of the two bodies via a spring. And that's going to be a potential that looks like this, where delta is the half length of the spring. Okay. So this is actually an exact analogy to mathematical analogy to this problem. And the mathematical analogy involves sending this frequency to the wave vector of this perturbation dotted into VA, where VA is the Alfvén velocity. Okay, so gamma squared is K dot VA squared. Okay, so these springs are magnetic fields that couple different bodies that are separated, different masses of fluid that are separated in radius. Okay. Okay, so now I'm going to set R is equal to some R naught. So here, the radius of the circular orbit is R naught plus some small quantity of order epsilon. And phi, the angular coordinate, is equal to some phase plus omega t. So there's the circular orbit plus y over R naught. So you can think of these bodies as being at a separation x and y from their initial point on the circular orbit. All right, so now we say that each of these things are of order epsilon, and we expand the Lagrangian to second order in epsilon. Okay, so when you do perturbation theory, that's what you have to do. So that's, what happens to the first order terms is an exercise for the students. Okay. So L2 is this. Okay. So you can see some familiar stuff here. This is just the kinetic term. This is going to give us the Coriolis force. This is related to the tidal expansion of the effective potential around the circular orbit. And this is our spring. Okay. So then Euler-Lagrange gives us the equations of motion. And I'm running out of space. Okay, so we get the equations of motion. X double dot is equal to 2 omega y dot plus 3 omega squared x minus gamma squared x. Y double dot is minus 2 omega x dot minus gamma squared y. Okay, so this should look reasonably sensible to you. So here's the Coriolis term, here's tidal expansion of the potential, and here's the spring. Okay, so then we look for the modes. So we set x and y proportional to e to the minus I omega t, and we'll get a dispersion relation out of this. Okay, so that gives a dispersion relation which looks like this. Okay, and I can't stress strongly enough, this is exactly the MHD dispersion relation when the field is vertical in the disk, and when we substitute k dot VA for gamma. Okay, it's exactly the same thing. Okay, and this we can solve. You can work this out in various limits, but there are two families of modes. So one family is stable. That corresponds to one root of a quadratic equation for omega squared. So if we take the small gamma limit, so gamma over omega is small, then there's one set of modes that basically doesn't care about the spring. This is when gamma is small compared to omega. There's one set of modes that doesn't care about the spring. It just goes around in epicycles in slightly eccentric orbits. And the other has omega squared is minus 3 gamma squared, so it's unstable. And you can look at the eigenvectors associated with those modes, and they involve the outer body moving backward. Sorry. Moving backward in its orbit. And so it's, let me pull this down. The outer body moving backward. The differential rotation in the neighborhood of this point looks like this. So if you push one of the masses outward, it falls backward in its orbit. Okay, it's a natural orientation. And so the spring pulls forward on it and adds angular momentum. But if it adds angular momentum, it wants to be in a higher orbit, right? So then it moves further out. And this is a runaway process. And this is what drives the MRI. Okay, so again, there's a Mathematica script in the files I prepared, and it does this problem for you so you can follow it in detail. The solutions to this thing look like this. And down here, the MRI goes away when the characteristic frequency is sufficiently high compared to omega, greater than 3 omega, root 3 omega. And that happens just because the spring is too strong. So the spring begins to dominate the dynamics, and it just wants to sit there and oscillate and have slightly modes that are slightly modified by rotation. There's a maximum here at 15/16 where the growth rate is a maximum, and the maximum growth rate is 3/4 omega. Okay, so this is what makes the MRI good for driving turbulence in disks. It's always dynamical. You can almost always adjust the wave number k so that for given field strength, you can almost always adjust the wave number k so that you're sitting right on this sweet spot, and the instability grows extremely rapidly, dynamically. The only time when you can't do that is when the field is very strong, when it's super thermal. Then these modes that sit here want to have wavelengths which exceed the scale height of the disk. So you then cannot fit the unstable modes inside the disk. Okay, so very, very strong fields can suppress MRI. All right. So what we know now about MRI is that it induces turbulence. So I showed you the animations already. Let's see. So this turbulence is driven by the MRI. We do not understand why the MRI saturates where it does. So there's some evidence from numerical simulations that viscosity and resistivity can influence the saturation level of the MRI. There's evidence that the saturation level, the relative strength of the magnetic pressure and the gas pressure depends on the ratio of viscosity to resistivity, which is known as the Prandtl number, magnetic Prandtl number. And I think that there's also evidence that the saturation level depends on the thermodynamics of the disk, so the vertical entropy profile of the disk, which in turn depends on energy transport inside the disk. And in Isles simulations like these, I would say that there is not good evidence for convergence. There is not good evidence for convergence for an isothermal disk. Okay. Yes? Okay, so let me try and expand on that a little bit. So if gamma squared over omega squared is greater than 3, the MRI goes away. Okay, so gamma is analogous to k dot VA. Okay, so for k dot VA squared over omega squared greater than 3, the MRI goes away. Okay, so this is like VA over lambda omega squared, where lambda is the scale of the instability. And so this means that for VA squared greater than about 3 lambda squared omega squared, the instability will go away. And then the largest length scale that we have available is the disk scale height. So that means that for VA greater than about 3, and the scale height is CS over omega CS squared, the instability will go away. Now, there are almost certainly other instabilities present. I mean, once you have a really strong field, there's lots of ways that the field tries to rearrange itself to minimize its energy. But the MRI will not be one of those ways. Okay. Yeah.
Do you have any comments on the anisotropy?
Yeah, so there have been numerical studies of this. One can look at correlation functions for, say, the magnetic field, and the correlated regions tend to be elongated ellipses that form trailing spirals inside the disk. And those ellipses, actually the orientation of those ellipses is well constrained. It's somewhere between 10 and 20 degrees to the line of constant radius. So these are very swept back spirals. The correlation in the minor axis, correlation length, tends to be very small. And that's another thing for which there's not good evidence for convergence in the numerical simulations, at least in the Isles models. Yeah. If you put in okay, so I should back up. I'm being a little bit too pessimistic here. If you put a mean field in the disk, then there is a characteristic scale, and it does converge. If you don't put a mean field in the disk, as we did not over here, then there's no characteristic scale, and that's a situation where you don't see convergence. Also, if you don't put a mean field in, but you do turn on microscopic diffusion coefficients, so resistivity and viscosity, you again see convergence. Okay, yeah. Yeah, so we're going to relive the development of accretion disk theory in the 1970s here, but yes, so that is an excellent question. And I think what you're suggesting is that the strength of the turbulence should be related to the local temperature. And that raises the possibility of what's called a thermal instability, where there's a runaway. So you turn up the temperature a little bit, that increases the heating rate, which then increases the temperature again, and you can have a runaway. One of the central questions for black hole accretion disk theory is why we seem to see quiescent disks around rapidly accreting black holes when they should be unstable according to the alpha model and according to recent radiation MHD simulations of the same disks. There have been, Yanfei Zhang has been a leader in this, of course. And those also seem to show the presence of thermal instability even in ab initio model, which does not assume an alpha model for the viscosity. Okay. All right, so I have one more model to do, and then I'm going to stop with this. The model is the so-called ADAF model. So we've got Bondi, we've got thin disk, which allows us to calculate a lot, but leans heavily on our knowledge of alpha. And we also have so-called ADAF models. How many of you work at CFA? Okay, one. Okay, not an unusually small number of CFA people at any, a typical astronomical gathering. So Ramesh Narayan is the originator with his postdoc Insoo Yi of these models. And this acronym stands for advection-dominated accretion flow. Okay, so the idea is, let's see, we have Bondi, which is spherically symmetric. We've got thin disk, which we describe as geometrically thin and optically thick. And then we have the ADAF models, which are sort of an unholy cross of the two. And so the ADAF models look like this. Okay, so they're geometrically thick. And in some cases, at very sub-Eddington rates, are optically thin. Okay, and so let's imagine we turn down the accretion rate so that these things which were optically thick become optically thin. And then eventually they become incapable of cooling as fast as they're being heated by the accretion flow. So at that point, we imagine that they'll puff up and they'll become really geometrically thick with h over r about 1 and look like this. So these things are quasi-spherical, but they still have some angular momentum in them. And the angular momentum still controls the accretion rate. Okay, so so what's new here is that we throw away the cooling for the most part that we included here, and we turn on an advection term in the equations of motion. So a term that looks like this. Okay, so in the thin disk models, VR is small compared to the sound speed. And so we can just neglect this. It's higher order in h over r. But in these thick disk models, h over r is of order 1, and we can no longer neglect this. Okay, so the strategy here is to write down the mass conservation, radial momentum equation, and the energy equation, and to adopt the ansatz that all of the dependent variables have a power law dependence on radius. So in particular, we assume that density goes as r to the minus 3/2. The radial velocity goes as r to the minus 1/2. That the orbital frequency goes as r to the minus 3/2. And that cs squared goes as r to the minus 1. Okay, so we can insert these in the basic equations, and what we're left with is a set of algebraic relations between the coefficients of these quantities. Okay? This is a very sort of high-level gloss, but for details, there's a very clear paper by Narayan and Yi, 94. Okay, so this allows us to solve for the coefficients of these things. And for example, we find that VR is equal to minus 3 over, just to give you a flavor for this, over 5 plus 2 epsilon prime alpha root GM over R. Okay, so this alpha is the same alpha that we've been discussing already. It's alpha associated with turbulence in the disk. And this dimensionless coefficient depends on two things. It depends on the adiabatic index of the flow, and it depends on how thoroughly we eliminate the cooling. So in particular, the ansatz here is that in the energy equation, there's a term which is heating minus cooling. And the ansatz is that this is equal to some constant F times the heating rate, okay, where F goes from 0 to 1. And this epsilon prime, again, just to give you a sense for how this goes, is 1 over F 5/3 minus gamma over gamma minus 1. Okay, so you can see that the radial velocity here is just alpha times the orbital velocity, roughly speaking. So this coefficient is of order 1, typically. Okay. So, so this attracted a lot of attentions. You know, this paper has in excess of 1,000 citations, and there have been many variants of this proposed over the years. And I would say that the language that people use now is to say that any model in which radiation is not playing a role, there's no cooling, is called a REAF, a radiatively inefficient accretion flow. So the ADAF is a special example of that. Another example of that is a model generated by Blanford and Begelman called the adios model, which I think was meant to say adios to the ADAF. And adios stands for, well, this stands for advection dominated, obviously. Inflow, outflow solution. Okay, so in these models, one imagines that material is coming in the equator, and then there's a magical wind that comes off the disk, which somehow is also self-similar. I would be happy to tell people stories about adios over beers. So there's a wind that comes off the disk, and this allows one to have a more general set of density profiles, not just having density scale as r to the minus 3/2, but having density scale somewhere between r to the minus 3/2 and let's say r to the minus 1. Okay. So in these models, the mass accretion rate, defined as the inflow rate in the disk, varies with radius. Okay. Evidently I said too little about that to enable people to ask questions. So I think the main message is that there are these geometrically thick, optically thin solutions, which are appropriate for very sub-Eddington flows. They're radiatively inefficient, meaning that the entropy that's produced by dissipation of turbulence remains in the flow and is then carried in across the event horizon at the end of the day. Okay, and I have a nice figure to sum this all up. This is from a talk that Mitch Begelman gave at Solvay conference 5 years ago. And so this is a Reesian diagram. Has anyone seen Martin Rees's diagram for all the paths that make a black hole? Okay, so Mitch was comes from the Rees School of Astrophysics, so sums things up with a flow chart like this. So black hole accretion, is rotation important? If rotation is not important, we can think about Bondi flows. If it is important, we can think about centrifugally choked flows or centrifugally supported accretion flows. By the way, now I think there's something that's in between these, where at the outer boundary of the accretion flow, one supplies lumps of gas with a distribution of angular momenta. And that material can, if those lumps are big enough, can make its way in new and interesting ways. And I say that based on recent work by Sean Ressler and his collaborators, his advisor, Elliot Quadiert, in modeling the galactic center. Okay, so over here we wind up with Bondi. Over here we wind up with a centrifugally choked flow, which is either radiatively efficient. So here are the reafs, or if it's radiatively efficient, we wind up with a thin disk model. If it's radiatively inefficient, it can be either quasi-Keplerian, yes, in which case we wind up with an ADAF or adios, or no, in which case it's like almost like a spherical star, possibly with a narrow funnel. And then in the thin disk case, or the thick disk adios case, there's a further question of whether the central object is spinning and whether there's strong magnetic flux, which is something I'll get to in just a second. Okay, so this flowchart is designed to get you to a jet, and that's where we go next. Okay. Can I get this up on the central screen? Hey. This is not like the University of Illinois. Okay, so all right, so those are the classical phenomenological accretion flow models. So now I want to turn to numerical models, and these can treat either thin disks, where radiation forces are important, and I'll let you talk to Yanfei Zhang about those. At the moment, I'm more interested in the thick disk, very sub-Eddington models. And I'll just show you some simulations of a subset of our models. So this is a relativistic MHD simulation of an initial centrifugally supported torus around a rotating black hole. And this torus has a significant amount of magnetic flux that penetrates the inner rim of the torus. And what you're going to see is the evolution of the rest mass density. So color here shows the log of the rest mass density. And I'm about to run out of time here. I think I have 15 minutes left. So let me zip through this stuff. Oh. Okay, so it takes a little while for this to go through. This is a slice through the poloidal plane, and this is an equatorial slice. And this is a high magnetic flux model, which is known as a MAD model. And MAD stands for magnetically arrested disk. Okay, so one of the important parameters of these models is how much magnetic flux is trapped in the black hole. Okay, so this would be a good opportunity to talk about this distinction between magnetically dominated models and non-magnetically dominated models. So these fall into two classes. There are the so-called MAD models, which are magnetically dominated, and the so-called SANE models, which stands for standard and normal evolution. And I credit all of these acronyms to Ramesh Narayan, so you can go talk to him if you have any complaints. So, so low magnetic flux or high magnetic flux. The idea is that magnetic flux tends to be naturally advected by the flow into the black hole, and and the flux just accumulates, or may just accumulate there. But there's a limit to how much flux can accumulate inside the black hole, because obviously, if you have so much flux in the hole that the energy vastly exceeds the binding energy of the plasma that's around the black hole, then it can just blow the plasma away and reach a lower energy configuration. Okay, so the question is, what is that maximum flux that you can trap inside the hole? And this is something that Sasha Tchaikovskoy, who's been a pioneer in this work, can discuss with you. I think he's going to be here next week, later on. So the natural calculation to do is to say we're going to be able to blow away the external plasma when the magnetic pressure exceeds the ram pressure of the accreting material close to the black hole. And the ram pressure is something like rho c squared. It's like the rest mass of the accreting plasma, okay? And now we've already done this estimate where we say m dot is 4 pi rg squared rho c. Okay, so in making this estimate, I'm going to take this and cast it in terms of m dot instead. So I'm going to eliminate density in favor of m dot. So this is m dot over 4 pi rg squared c times c squared. Okay, so this lets me estimate the critical magnetic field strength in terms of the mass of the black hole, which is buried in this Rg, and m dot. Okay, so instead of casting this in terms of a magnetic field strength, I want to cast it in terms of the magnetic flux through the event horizon. Okay, so I can integrate B over hemisphere of the black hole and find out how much magnetic flux is trapped in the black hole. Okay, so some of you may worry about having magnetic flux in the hole. It's not a property of the black hole itself. We know that black holes have no hair, right? But they can wear a plasma toupee. And so these fields are supported by currents in the plasma around the black hole. And so this field is a property of the accreting plasma rather than a property of the hole. Okay, so I want to calculate the flux, which is of order Rg squared times B, because this area is of order Rg squared. Okay, so that means that B is order phi over Rg squared. And this allows me to estimate a characteristic flux where the accretion flow can no longer trap the field in the hole. And I get it by substituting this in here. Phi over Rg squared is of order m dot over Rg squared c times c squared. Okay, I've dropped all factors of order 8 pi. Okay, so this implies that phi is of order square root m dot Rg squared c. Okay, so this is phi critical. And this leads us to define a dimensionless magnetic flux. And I'm running out of room here. A dimensionless magnetic flux phi, which is the actual flux over the critical flux. And we can only assess what the maximum possible value of this is by numerical experiment. So there's no analytic theory for this at the moment. And what you find is that phi of about 15 in the right units is the critical flux, is the maximum dimensionless flux that can be sustained by the accretion flow. Okay, so I have 6 minutes left, and yeah. Oh, I have 36. Oh, good. Okay. Oh, thank you. Okay, good. That's great. So let me show you some more numerical simulations then. And then we'll talk about Blandford's Nyack and some open questions. Okay, so I'll put this down. So this shows another view of some of the simulations that I just showed you. Color again here is showing the log of the rest mass density, but this time on a spherical surface at 10 GM over c squared. And this shows a set of 4 different models, some of which are sane and some of which are mad. And so the mad models have this dimensionless flux of 15, and the sane models have dimensionless flux around 1. And then the spin of the black holes is either negative, so these are strongly retrograde disks, or positive, so those are strongly prograde disks on the other side. Okay, so I want you to notice a couple things about these models. One is that the mad disks are really crazy. So so you can see these events where flux bubbles out through the disk and it produces low density regions at the midplane. So these are flux tubes that are making their way out through the accretion flow. And let's see, there's one right there, right there. Again, this is just a spherical surface, so material comes out through the surface or can pass in through this surface. Another thing that you can see in these images is that the sane models tend to have, well, all the models have empty regions over the poles. Okay, so obviously, I didn't say this, but I think it's obvious that the equator is here and the North Pole, the accretion flow is here. Okay. So all these models have empty regions over the poles, which are known as the funnel or sometimes the jet or the pointing jet. And you can see that the funnel is wider in the MAD models than in the corresponding sane models. So this kind of makes dynamical sense that if you have a strong magnetic field embedded in that funnel, it can push aside the disk and make a wider funnel over the hole. So the field lines that are sitting in here go down into directly down into the black hole. They don't attach to the disk. And so there's really nothing to support plasma in that part of the flow. If you put plasma on that field line, it'll either go in to the black hole or go out. Okay. So the other thing that you can see is that something is making the plasma in the funnel here rotate one way or the other. And in these retrograde cases, you can see there's material at the edge of the funnel here. So this is a MAD, strong magnetic field model. You can see the material is being dragged around in this direction while the accretion flow itself is flowing this way. Okay, and that rotation is connected to directly to the rotation of the black hole. So the black hole is dragging field lines that are embedded in the event horizon with it and forcing those field lines to co-rotate with the black hole. Okay, so that's the origin of the so-called Blandford's Nyack effect, is dragging field lines that pass through the event horizon by the rotation of the black hole. Yeah. Yeah. Yeah, but they evolve on a fairly long time scale. So if you have a lined accretion, then you can change the spin only basically on the saltpeter time scale. Yeah. That's a really good question. Yeah. So this gets back to the question of alignment of accretion flows in galactic nuclei. There doesn't seem to be very good evidence for alignment. And so you can imagine that if the flow, you have a disk that's accreting onto a black hole and the orientation of the disk is randomly moving around over time, that sometimes it'll be prograde and sometimes retrograde, and that the net effect over very long time scales will be to despin the black hole. Okay, so these are fluid flow models. And let's say you had a resolved image of a black hole accretion flow, then you would want to calculate what these things look like. And so I just have to show this. So this is from Event Horizon Telescope. We built a lot of models. And each of these models makes different assumptions about the state of the plasma in the accretion flow. So in particular, the electron distribution function. And that's what you need to understand the interaction between the accretion flow and the radiation field and to produce a synthetic image that you can compare with data. So one of the key questions in this field is, what is the microscopic state of the plasma inside these accretion flows? Is the electron distribution function thermal? If it's thermal, what's the temperature? Is it non-thermal? How do we model that? Okay. Yeah, I have some prettier images here. But before I talk about this, I want to talk about, actually, let me turn that back on. I want to talk about Blandford-Znayak effect. So I was going to talk about relativistic MHD. Do people want to see? So I don't have that much time left. I can't do both. Should I do relativistic MHD or should I do BZ? Blandford-Znayak, yeah. Right. Okay, so yes. So when the accretion rate is very low in m dot, in the sense that m dot over m dot Eddington is small compared to 1, we think that the accreting plasma is collisionless. So that means that the mean free path to Coulomb scattering vastly exceeds RG. So in the case of models for M87, it's sort of 10 to the 5 RG. So this is the large Knudsen number regime. But this is also a magnetized plasma, which means that the excursions of individual particles perpendicular to field lines are limited by their gyro radius. Okay, so in 2 dimensions at least, we expect that it might behave something like a fluid. Along the 3rd dimension, along the field lines, one really doesn't know what to do. And one approach to this is to look beyond MHD and start to include non-ideal effects like heat conduction and viscosity. And there's some work that I did with my student Mani Chandra and also with Francois Foucard, who's going to also be arriving today, Monday. Okay. So with Francois Foucard and Elliot Quadiert, and we looked at these sort of extended MHD models to try and assess how much the flow would change. So the outcome of that is a little bit complicated, but because one still needs to introduce a closure. So the idea is that you're not allowed to do absolutely anything you want with the distribution function. If you make it too anisotropic, it'll fall apart. There are kinetic instabilities that will re-isotropize the distribution function. And so we had a closure model for that, which needs to be tested in kinetic simulations. But the upshot was that conduction is probably not important, and viscosity can be important, but it turns out that the viscosity, which is in these plasmas, or in all plasmas, is equivalent to anisotropy in the distribution function, the viscosity behaves exactly like the Maxwell stress, the turbulent Maxwell stress. So when we do an ideal MHD simulation, we calculate one level of turbulent Maxwell stress. And when we do a viscous simulation with viscosity constrained to be along the field lines, we get exactly the same stress, but part of it's viscous and the rest is Maxwell. So it's a complicated story. Yeah. Yeah. Sure. Yeah. So what can I say about this? So for isothermal models, isothermal models tend to produce alpha of order 0.05. Alpha is just a scaling relation, right? So it almost has to obtain in these shearing box models. So you get a dimensionless strength of the turbulence around 0.05. There's also evidence, again, that this depends on the vertical field strength. So if you put a vertical field into your box that you use to simulate this, you tend to get larger alphas. It depends on the magnetic Prandtl number. It also seems to depend on how strong convection is in the disk. So there are people working now on models for cataclysmic variable disks that include realistic opacities. And so cataclysmic variable disks are binary systems where there's an accreting white dwarf, so with a mass-losing companion. Those disks seem to produce a variable alpha depending on what the temperature of the disk is, so how convective it is. When it's more convective, alpha tends to be higher. When it's less convective, alpha tends to be lower. But again, there's always worries about convergence in this business. So don't tell anyone I told you that alpha is 0.05, because I didn't. Okay. So Blanford-Znayak. So we've already done the limiting magnetic flux. And now we want to ask what happens when you embed that magnetic flux in a rotating black hole. And this is a problem that was first considered by Blanford and Znayak in 1977. So I think many of you know that Penrose considered methods of extracting energy from a rotating black hole in the late 60s. Blanford and Znayak were the first to, I think, propose an astrophysically realistic scheme for getting energy out of a rotating black hole. And Blanford and Znayak considered a force-free model. So force-free here means that the density is very low, but it's not so low that we're in the vacuum electromagnetism regime. So there are still charges around that can carry currents. And that means we're still in a regime where the ideal MHD condition applies. So ideal MHD relates E and B. It says that E is minus V cross B on C. Okay, so it takes the number of degrees of freedom in the field from 6 down to 3. Okay, and so this is a relativistic version of that. And yeah, so J cross B is 0, yeah, yeah. Yeah, so, yeah. So what Blanford-Znayak did was say, let's look at a field configuration for a non-rotating black hole. Okay, so Schwarzschild, and we're going to use a monopole configuration. Okay, so field is just coming out. And if you want to make this more realistic, you can use a split monopole where it goes in one hemisphere and out in the other. And then don't worry about what happens in the equator. Okay, so so the idea was to spin this up and do an expansion of the equations governing the magnetic field in the limit that the spin of the black hole is small compared to 1. Okay, and that's the analytic hook that lets you get a solution. So the equations that you solve are the source-free Maxwell equations and the stress energy conservation. So this is actually why I was going to do relativistic MHD first, because this makes more sense. But you have source-free Maxwell, so the induction equation, and then you have divergence of T mu nu is equal to 0. So these two equations allow you to evolve the magnetic field in this force-free approximation in the magnetosphere around the black hole. Okay, so this is a mathematically challenging task for which you need an understanding of polylogarithms. But I think it's really a simple idea, which is that you have magnetic field lines embedded in a rotating body. And when the body rotates, it drags the field lines with it, and that causes energy to be carried away from the rotating body. Okay, so we can estimate how big this is, how big the energy flux is. And we're going to call that the Blanford-Znayak luminosity. Okay, and the way we do that is to take the Poynting flux at the surface of the black hole. Okay, and LBZ is going to be equal to the Poynting flux times RG squared. I should twiddle that, it's not equal. Okay, so that begs the question, what's the Poynting flux? Okay, so MHD Poynting flux, so we know that Poynting flux is equal to C over 4 pi E cross B, right? And we also know that E is minus V cross B on C in the ideal MHD approximation. So this is C over 4 pi minus V cross B over C cross B. And then with the aid of some identities, we can rewrite this as B squared V minus V dot B B over 4 pi. Okay? And the piece that's relevant here at the event horizon is not this piece, because the VR is actually inward on the horizon. It has to be inward on the horizon. So we'll consider this piece. Okay, and we'll say that the velocity at the event horizon is just rotation. Okay, so there's an rotation frequency, and I don't want to completely erase this because I'm going to need that in a second. There's a rotation frequency, so we need S is V dot B, which is of order RG omega, times B phi times BR. And I'm doing this all in a totally Newtonian view, okay? So when the thing isn't rotating, the field is entirely radial. When we turn on rotation, we get a little bit of B phi out, right? So that allows me to estimate, this is RG, and then omega is A times C cubed over GM. This is just 1 over TG, the characteristic time scale, light crossing time. Okay, so, and then B phi is just, we'll just say it's of order A times BR. Okay, well, on the idea that when A is 0, B phi is 0, when I turn on A, at lowest order in A, we begin to get a B phi. Okay, so this gives me a full expression for the Poynting flux. It's just A squared, and then this times this gives me C, times C times BR squared. Okay. This, I'm sorry this is so hand wavy, but actually doing this rigorously is a mess. Okay, so this gives us the Poynting flux here, and then we can finish this estimate. So what we get there is A squared C B squared times RG squared. Okay, so that's the Blandford's-Nyack luminosity. Okay, so now let's try and connect that. So this is, right now, this just tells us that it's related to the magnetic field strength. But we know, at least for most of the sane and mad models that we've looked at, that the magnetic field strength is connected to the accretion rate, right? And in fact, it's connected through this characteristic value for the accretion rate. So what I'm going to do is write B in terms of the magnetic flux, and then I'm going to write the magnetic flux in terms of this dimensionless flux phi and this characteristic magnetic flux. Okay, so let's carry out that program. So I still have my A squared out front. I have C, and then B is phi times phi crit over RG squared times RG squared. Okay, so phi crit squared. So let me okay, so phi crit squared is RG squared m dot C. Okay, so this is okay, and then let's see, I'm missing no, I'm good. Times RG squared divided by RG fourth. Okay, that's RG fourth, RG squared, and RG squared there. So all the RGs go away. Okay, now at the end we get A squared, phi squared, m dot C squared. Okay, so this tells you that the Blandford's-Nyack luminosity is proportional to the accreted rest mass energy, and that the efficiency is directly related to the square of the spin and the ratio of this magnetic flux to the critical magnetic flux. Okay. Yeah. Yeah, it doesn't matter. So if you look at the simulations I showed a little earlier, you can see that the funnel plasma is rotating backwards in one case and forwards in the other case. And the rotation frequency of the field lines in the funnel is actually directly related to this. It's directly proportional to the spin. Does that, there's something that's bothering you clearly that I'm not. Yeah, so right, so the critical magnetic flux, the, the dimensionless magnetic flux, which is the maximum possible value, is actually slightly different in the two cases. It's slightly lower in the retrograde case, yeah. But that I haven't made any assumptions about that here. So phi is what phi is. Okay. Yeah.
You would only expect to see a very small fraction of this luminosity, right? Because this is it's pointing flux, which is mostly silent. So.
Yeah, it's well, if that were true, then we wouldn't see pulsars. So the
a small fraction of this will actually be observed.
yeah, so I think that the answer to that rests on unresolved problems about what happens to these pointing jets as they propagate outward. And there are a couple of things that could happen. So one thing that could happen is that the field lines could be loaded by various pair production processes with electron-positron pairs. Another thing that could happen is that plasma from the surrounding medium could diffuse in to the pointing jet. And then a final thing that could happen is that you might have a shock, which again induces pair production, which produces pairs that can then radiate. So ultimately, we may recover a substantial fraction of the energy. Yeah, so in the case of, just to give you a concrete example, the X-ray luminosity of M87 right now is about, if I remember correctly, about 10 to the 41 ergs per second. And the jet luminosity, if it is a pointing jet like this, then this is relevant, is greater than 10 to the 42 ergs per second. So, and that's estimated in a number of different and equally inaccurate ways. So one way people estimate the time averaged luminosity of the jet is by asking how much PDV work does the jet have to do to excavate the observed cavity in the intercluster or intergalactic medium, and then divide that by a lifetime for the jet. And that produces estimates for the jet power, which are actually substantially above 10 to the 42. So some of this energy may go into excavating a cavity. Some may go into radiation, depending on how the jet is loaded. Yeah.
Is there any models or simulations on the alignment or misalignment among
Yeah. So that's a really interesting problem. Matthew Liska has recently produced some interesting simulations of misaligned disks. I should back up a second and just say what the classical theory of the misaligned disks is. So there's something called the Bardeen-Pedersen effect, which is Jim Bardeen, not John Bardeen. And that makes the observation that if you think about the accretion disk as a series of rings that are tilted out of the equatorial plane, then each of those rings will precess due to lens tearing effect. And the precession rate will depend strongly on radius. And so that will wrap up the warp with radius. And then if there's any sort of dissipative coupling between neighboring rings, and you can wait long enough, then those rings will settle into a common equatorial plane where they're not precessing anymore. So how that happens depends on how that coupling occurs and what waves are present that also might excite tilt or cause tilt of the disk to decay or be carried away. So there's an idea, going back to the Bardeen-Pedersen paper, that the disk will naturally align everywhere inside a characteristic radius, which is called the Bardeen-Pedersen radius. And then this theory has been revisited again and again over the years. Have you done something on that, Phil? Everybody's worked on that. It's a really interesting problem. And I would say that the outcome is not yet clear. That there's a suggestion that the behavior of the disk depends on the ratio of alpha to the dimensionless thickness of the disk to h over r. So that's who did that stuff? Is that Pavloiza and Pringle? Probably, yeah. And then there have been simulations. So only recently has it been possible to do this in MHD simulations. And a recent example is Matthew Liska's work. Matthew Liska's work suggests that there actually is gradual alignment even of a thick disk, and that the jet emerges perpendicular to the disk and not along the spin axis of the black hole. So you can think of these pointing jets as like, they're very light, right? They are light. And so they're easy to deflect. So it's kind of natural to think that it emerges perpendicular to even to a tilted disk.
In the EHT results, they seem to assume a alignment between the jet
Yeah,
and the
yeah.
spin.
Do you have a problem with that? Yeah, so that's because the tilted models are really expensive and not yet fully understood. So it increases the dimension of the parameter space by 2, and that makes things really hard. So I think the real reason it was ignored was practical. But if I had to make an excuse for that, I would say that there really isn't good evidence for precession of the jet. At least if you go far enough out, the jet seems to have been aligned in the same direction for an extended period of time. Okay. I'm kind of talked out. Happy to talk. I'm here for another 2 weeks.